Well, let's start off with a funny story here. I just got finished recording this amazing lesson. Everything was so well articulated and explained well, and I somehow canceled the saving and now it's gone. So here we are starting over again. Hopefully I can explain things well here. So here we're doing lesson 5.1, polynomial equations. Back in chapter 2, we worked with polynomial functions, and we learned several strategies for factoring polynomial functions. And we're going to use a lot of those same strategies as we work with polynomial equations and trying to solve equations. In this chapter 5, what we're doing is we're going to be solving equations that deal with a lot of the functions that we learned in chapters 2, 3, and 4. So polynomial functions and rational functions and square root functions, exponential functions, logarithmic functions, trig functions. We looked at those functions. Now we're going to be solving equations that deal with some of those different things. So in chapter 2, we learned strategies for factoring polynomials. Some of the things we used were the factor theorem, complete linear factorization theorem, the remainder theorem, we used synthetic division, and the rational root theorem. So let's do a quick review of those things. The factor theorem says if p of r equals 0, where r is a real number, then x minus r is a factor. So really what that's saying is if you plug some number into a polynomial and you get 0, x minus that number will be a factor of that original polynomial. Next thing is the complete linear factorization theorem. It's written here, but the idea is if you have degree n, a polynomial with degree n, you will have n linear factors. So if there was a polynomial with degree 7, you'll have 7 linear factors. Degree 3, you'll have 3 linear factors. Next is the remainder theorem. If a number a is substituted in for x into a polynomial, p of x, the resulting value p of a equals the remainder obtained when the function is divided by x minus a. That's just saying if you plug a number into a function, you can find the remainder if rather than doing the division problem. Sometimes it's helpful, but since we have synthetic division, a lot of times doing the dividing is quicker. The last one, the rational root theorem, several lines written here, but the idea is you have a polynomial. This represents a polynomial of degree n. This one's just saying if there's a rational factor, it's going to be in the form c over d, where c is a factor of the constant and d is a factor of the leading coefficient. We used that often back in chapter 2, and we'll be using that again here with solving polynomial equations. And the other thing, synthetic division, which we'll practice here in this next example, we use it often. So let's look at that and practice this synthetic division. Now what we do for synthetic division, we're going to use these coefficients, 3, -8, 5, -2. If there were a 0 term here, if there weren't an x squared here, we would make sure we put in a 0 where an x squared coefficient would go. But all the coefficients are there, so we're going to list them 3, -8, 5, and -2. And we want to try each of these 4 numbers to see if they're roots of the equation. Do you remember what we're going to look for if we're looking for roots of the equation? We're going to look in this column here, and when we look in this column here, we're looking for a 0. Because if we get a 0 as a remainder, that means it's a root of the equation. So as a review, to do synthetic division, you bring down the first number, and then just after you bring down the first number, it's multiply, add, multiply, add, multiply, add. So we're going to bring down the 3. We're going to multiply -2 times 3 and add it to -8. here's the numbers right here. It comes up kind of quickly. We'll talk through it. We bring down the 3. Negative 2 times 3 is negative 6. Negative 6 plus negative 8 is negative 14. Then multiply and add again. Negative 2 times negative 14 is 28. Then add to 5, you get 33. Now we're going to multiply and add again. Negative 2 times 33 is negative 66, and add negative 2 to that, you get negative 68. So that was synthetic division. Obviously, we're going to do these 3 more to get some practice. So is negative 2 a root? No, because we didn't get a remainder of 0 here. Let's try negative 1. We're going to bring down the 3, multiply, and then add. So negative 1 times 3 is negative 3, plus negative 8 is negative 11. Negative 1 times negative 11 is 11, plus 5 is 16. Negative 1 times 16 is negative 16, plus negative 2 is negative 18. Still not 0, so negative 1 is not a root. We're getting closer, though. This was way down at negative 68. Now we have negative 18. We're moving our way up. Let's plug in, or try 1. So here's what you would get if you put 1 in. Bring down, multiply, add, and multiply and add. Get a remainder of negative 2. Getting closer to 0, still not there, so I assume that we'll probably get a 0 here. Bring down the 3, multiply and add, and we do get a 0. So therefore, 2 is a root of the equation. So since 2 is the only root of the equation, so 2 is the only root of the equation from the set that we were given. There obviously would be more. How many more would there be? Well, since it's cubed, we have 1 root. We need a total of 3 roots because of this 3. So there would be 2 more roots. And we could solve the depressed polynomial or the depressed equation here. Remember, if we were to rewrite this, after we divided, this was x cubed. This would be 3x squared minus 2x plus 1. Once you're down to a quadratic, you should be in good shape because you can either factor or use the quadratic formula. We use these other strategies to get down to a quadratic. So here's another example. Kind of helps us out a little bit. We want to solve this, but it's already telling us x plus 4 is a factor. Since x plus 4 is a factor, that means negative 4 is going to be a root, so we're going to do synthetic division and put in negative 4 to divide into there. So we bring down our 1 and our 4 and our negative 2 and negative 8. And we're going to put negative 4 here to divide by. And we're going to bring down, multiply and add, and of course we will get a 0 here because it told us it was a factor. We had our cubed polynomial. We divided, and so now this is down. Our depressed polynomial is squared. We can write the equation like this. I don't always write the x plus 4, and I just remember that negative 4 is a root, but you can write it there to remember. So these two multiply to equal 0. Remember back to, I think, Algebra 1, you probably learned if 2 things multiply to equal 0, one of them's got to be 0. Probably even learned that before Algebra 1. So we can break this up into 2 equations. Either this factor equals 0 or this factor equals 0. Subtracting 4 from both sides here would give us x equals negative 4. Over here to solve, we would add 2 to both sides. Take the square root. When we take the square root, we do plus or minus. So our solutions here are negative 4 and plus or minus root 2. And again, that's 3 solutions. 1, 2, 3. 3 solutions because we had degree 3. This next example here, they don't give us any of the help where they tell us one of the factors to start with. So we're starting from scratch, and we're going to work our way to factoring this thing. Once it's factored, it's easy to solve. So we're going to use our rational root theorem, which is the c over d. So we want to find the factors of 54, which are listed here. That's our possibilities for C. And then for D is our factors of the leading coefficient is 1. Well, the factors of 1 are just plus or minus 1. And what we want are all combinations of C over D, which means we want this over 1, this over 1. So really we're just doing all of these over 1, which just gives us those possibilities again. So these are our possibilities. We're going to start trying these possibilities with our synthetic division to see what works. So set up our synthetic division, put our coefficients here, 1, 3, negative 21, negative 9, and 54. Let's go ahead and get started trying some numbers. We'll start off with 1. I'm not really going to give you the time to think through and do all these synthetic divisions. Maybe I'll talk through this first one, but hopefully you have this down, especially with the reminder we just had. Bring down the 1. 1 times 1 is 1 plus 3 is 4. 1 times 4 is 4 plus negative 21 is negative 17. That goes way too fast for me. 1 times negative 17 is negative 17. Minus 9 is negative 26. 1 times negative 26 is negative 26 plus 54, and you get 28. So all of that to say 1 does not work because we did not get a 0 here. Let's go ahead and shoot for 2. If you do your synthetic division here, you would end up with these numbers, and we end up with a negative 8. Just as a reminder, we had a positive 28 here, a negative 8 here. Anyone remember what that means? We went from positive to negative, so somewhere between 1 and 2, it has to cross over 0, which means we will have a root between 1 and 2. Now, when we do this rational root theorem, this gives us all the possible rational roots, ones that can be written as fractions. We didn't have any fractions here, so it's not going to be a fraction, it's going to be probably a square root. Probably a square root of 2 or square root of 3, because that's what falls in between here. Anyway, that's just a reminder that you can tell if you have a positive to a negative, there will be a solution in between there. Let's keep going with our work here. Let's try our next one. Let's try positive 3. Positive 3, work our way through here. You get these numbers, and we end up with a 0. So 3 works, which means 3 is one of our solutions. Now, don't keep working with this now. Don't try 6, then 9, then 18, then 27. Don't keep going. We now had something that worked. We have a depressed polynomial or depressed equation. So now we want to work with something smaller. We'll work with smaller numbers. So what we have now, this was a polynomial with degree 4. Once we divide, now this is degree 3 or cubed. So now we can do synthetic division again. We can rewrite these coefficients 1, 6, negative 3, and negative 18. Also remember, 1 and 2 did not work to start with. They're not going to work again for this one because we're dealing with the same polynomial. It's just in a depressed form here. 3 might work again, so don't discard that. It did work. It worked once here. It could possibly work again. Also, one last thing about this before we move on to trying this. We have a new polynomial, a new constant term, negative 18, which we could do C over D again. So 27 and 54 are not factors of 18, so we would not try these two. The rest still are factors. And again, we wouldn't try 1 and 2 because they didn't work before. So let's just take a stab in the dark or whatever. And let's try negative 6. Bring down the 1. Get negative 6 plus 6 is 0. And we end up with a 0 as our remainder. Well, that saved us some time if you can just randomly choose a number and it works. Best of luck to you with that. But now we're down to a quadratic term. This was cubed. We divided, now this is squared. We can We now know 3 is a solution or a root. Negative 6 is a solution, also called a root. Now let's solve this last quadratic. We have x squared minus 3 equals 0. We could add 3 to both sides, take the square root of it, make sure you use plus or minus, and we get our solutions. So we're going to add 3 to both sides, take the square root of both sides, and we get x is plus or minus 3. How many solutions do we have? Well, we have 3, negative 6, and plus or minus root 3. That's 4 solutions, which makes sense because our degree was 4. Our last example here, 2x cubed plus 5x squared minus 2x minus 5 equals 0. Going to start off the same way. Just real quickly, degree 3. So how many solutions are we going to have? So what we're going to do here is we're going to use the rational root theorem, or C over D. So our possibilities for C are plus or minus 1 and plus or minus 5. Those are the factors of 5. Our possibilities for D are plus or minus 1 and plus or minus 2, the factors of the leading coefficient. So now for C over D, we want to take all possibilities of C over D. So we have 1 over 1, 1 over 2, 5 over 1, 5 over 2. Those are our possibilities and plus or minus for all of those. And so those are the possibilities there, and let's get started trying. Use our synthetic division, so we bring down our coefficients, 2, 5, negative 2, and negative 5. And let's go ahead and start with a positive 1. Bring down the 2. 1 times 2 is 2, plus 5 is 7. 1 times 7 is 7, plus negative 2 is 5. 1 times 5 is 5, plus negative 5 is 0. So 1 works. We had a cubic function. We divided. We're now down to a quadratic, so we can take our quadratic here. So 1 is a solution. Take our quadratic, 2x squared plus 7x plus 5. We can write it all as factors, or we could have just written this part. Just don't forget that 1 will be a solution. We can factor this. If you think through that, it does end up factoring. If you have trouble factoring, you could always go back to quadratic formula. But that does factor to x minus 1, then 2x plus 1, or 2x plus 5 times x plus 1. And then we can solve each of those. Either this equals 0, or this factor equals 0, or this factor equals 0. Solving each of those, obviously, this would give us 1. 1 minus 1 equals 0. Here, if you think through it, for this term we want negative 5, because we want negative 5 plus 5 is 0. Well, what here would give us negative 5? That would be negative 5 halves. If you can't do it that way, just do 2x plus 5 equals 0 and solve. And this one gives us negative 1. So our solutions are, once again, 1, negative 5 halves, and negative 1. That's a lesson. Hopefully a lot of that was just a refresher course on factoring polynomials, and then we solve them here, and you can go ahead and get started on your homework.